In this exercise 3, we're asked to find the solution to the given system of first-order linear differential equations. So the first thing that I would do is make sure they're first order. Well, let me see. They only have one derivative. They only have first derivatives here, and those derivatives are to the power of 1. The dependent variables, both here, are to the power of 1. And so we can say that they are linear. Also because their coefficients are all just with respect to a single variable. In this case, just constants. So what are we going to do? I would write this in matrix form. So let me do an arrow here. Let me say what I'm doing. Matrix form. So here, we're going to have an x prime, and here we're going to have a y prime. And this is going to be a vector. And here we're going to have the coefficient matrix, -4, 2, -5 over 2, and 2. And here we're going to have an x and a y. If it is unclear how I did that, just multiply these two together, and you'll notice that we can, because this is a 2 by 2 and this is a 2 by 1. And so as long as these numbers are the same, we can execute the multiplication, and these numbers tell us the dimensions of what we'll get as a result, which is indeed a vector, which makes sense, right? Because we have this right-hand side equal to the left-hand side, which is a vector. So now that we do this, how can we solve this? Well, I'm going to do a little bit of a review. And let's just say that we have this form right here, which we actually do. We can guess, because this is a first order with constants here, we can guess that a solution is let's say it is k e to the lambda t. And I will say that k is all made of constants. Then x prime is going to be k, the lambda in front, e to the lambda t. I just took the derivative of the part that varied in the expression, and then the constants stayed the same. Now I can substitute these back in, and what am I going to get? I'm going to get lambda times k e to the lambda t is equal to the matrix A times k e to the lambda t. Okay, so now what I can do is I can divide both sides by this, and then I can subtract ak to both sides of this equation. And I'm going to put the I matrix in here as well to make it compatible, because this is a matrix and this has to be a matrix. So now here we're going to have the 0 vector. We can factor out this k right here. What happens if we do that? Then we get lambda minus ai, and I made a mistake here. I wanted to, this is already a matrix. This is scalar multiplication, and I want to put the I here. So, oh, this eraser is not collaborating. Okay, here and here. So I want to put the I right here. Now, I can multiply both sides of this by -1. As long as I do everything to both sides of an equation, the equation doesn't change. And now I have ak k minus lambda I k right here. All of that is equal to the 0 vector. I can factor out, now I can factor out this k. What happens if I do that? Well, now I get a minus lambda I times the k vector is equal to the 0 vector. There's two ways that this can happen. Either k is equal to the 0 vector, and this is called the trivial solution. And we're often less interested in this solution because it's a little bit less useful. And then if the determinant of a minus lambda I is equal to 0, then that means that this term right here will make a non-zero vector collapse to a lower dimension and get to the 0 vector. So now let's apply this to this particular case. So we want to say that the determinant of a minus lambda I is equal to 0. Okay, so let's substitute what we have. Our a is -4, and to indicate determinant, if you use vertical walls, that means the determinant. So a is -4 and 2, and then we have -5/2 and 2. Okay. Well, I already see that this has the same entries for the columns. So I don't remember all the cases. It might be that this already is a determinant of 0, but we'll see. And then we want to subtract. So we want to take this, and I'll indicate the determinant in another way because I have multiple matrices, and I want to subtract the identity matrix, which is 1, 1, 0, 0 in this case, but multiplied by lambda. So we're just going to have lambdas multiplied by all the entries. With the 0, it just gets canceled out. And then let me move it a little bit more to the right. And then here, I want to find the determinant. And I want to make this determinant equal to 0. So if I subtract these two matrices, they're a 2 by 2 here and a 2 by 2 here. So I can definitely do that. I can subtract each entry, and I get the following. 2 minus 0 is just 2. Then -5/2 minus 0. And then 2 minus lambda right here. Now I can use those vertical lines to indicate the determinant. And all of that has to be equal to 0, which means that I'm going to factor out a negative, so that here we're going to have this times lambda minus 2 times a -1, because I factored out a negative out of that one as well. And then on the other side, we're going to have 2 times -5/2 right here. And all of this has to be equal to 0. Okay. So now these two negatives cancel out. And I can say that this is lambda squared minus 6, the sum of these two constants, times lambda, and their product is plus 8. And then here, the 2 and the 2 cancel out. The negative signs become positive, so we get a +5. And all of that needs to be equal to 0. And I'll move this to keep everything neat. All right, so now what do? Well, now let's add these two together. And we're going to get 8 plus 5, that's 13. And here, -6 lambda and lambda squared. Now, can you think? I don't think I can. Can you think of two numbers that add up to 13. No, that multiply to 13. Well, 13 is a prime number. And so it's either we did something wrong here, or this is going to be complex roots. Well, let's see. We are over here. We're subtracting lambda, so we get -4 minus lambda, 2 and -5 halves, and 2 minus lambda. Right. So now this and this is going to become lambda. Okay, I see a mistake here. This should be a +4 because I factored out a negative sign. So if we have a +4, then we're going to get a +4 times -2, which is going to be a -8 here. So this one's going to be a -8, and their sum is actually going to be a +2. So this one's going to be a +2. So let me rewrite these two. This is going to be a +2, and this is going to be a -3. So now, can you think of two numbers that multiply to -3 and add up to 2? Well, I just wrote them. If I multiply -1 and 3, I get -3. If, on the other hand, I add them together, I get a +2. Good. So now we have that our two eigenvalues are 1 and -3. Now what we want to do is we want to find the eigenvectors. So we want to plug the eigenvalue back into this. We want to find the eigenvector, right? So we want to find this. Sorry. We want to find, for each eigenvalue, we want to find, I don't know why I keep doing that. It's going to be a minus I lambda times k. It's going to be equal to 0, and we want to find this k. We're after this. We're after this. Okay, let me just show you where we're at so far, right here. Okay, so how do we do that? Well, if we know what lambda is now, so we can plug it back in, and it's basically going to be that original matrix minus the lambda and the actual value of lambda. So we have lambda 1, so it's going to be -4 minus 1, which is going to be -5. Then we're going to have that 2 that stays the same. Then -5 halves that stays the same. And finally, we're going to have 2 minus 1, which is just going to be 1. Now we close this, and we put the k, which we can say our first component and our second component of k, where k without the arrow on top is a scalar. And then the 0 vector has all entries of 0. Now, how do we solve this? Well, there's a couple ways. We can do substitution, since this is small, and it would be a system of two equations, two unknowns. We could use the augmented matrix to solve it, or the inverse matrix if this has an inverse, which I don't know if it does. Actually, you cannot use inverse because this has been engineered to have a determinant of 0, and the determinant of 0 matrices are non-invertible. So, but you can use the augmented matrix. I'm going to use substitution in this case. So I'm going to multiply each of them. K2 is equal to 0. And I really only have to do it with one row, because if I do the other one, look at what we get. We get a multiple of this. We can get to this by dividing by 2. So this second equation doesn't add any new information. So I'm just going to use the top one, and I'm going to say that K1 is equal to negative 2, well, actually positive 2/5 of K2, which means for K2 equal to 1, K1 is 2/5. Or let's say K2 equal to 5. So we have all whole numbers. K1 is equal to 2. And this is going to be our K1 vector. We can do a similar process for the other value. So what was the other value? For lambda 2 equals -3. Now we're going to input it back into our expression here, and we're going to have -4 minus -3, which is -4 plus 3, which is -1. We have that 2, that 5/2 here with a negative in front, so -5/2. And then finally 2 minus lambda. 2 minus -3 is 2 plus 3, which is 5. So we're going to have a 5 right here. Then we're again going to have your K1 and K2 here, not to get confused with the other K1s and K2, or you could choose some other variables. And here you're going to have the 0 vector. Now, same as before, we're going to have two linearly dependent equations. So we can just use the top one and say -K1 plus 2K2 equals 0, which means that K1 is equal to -2K2. So for K2 equals 1, K1 is equal to -2, which means that our K2 vector is going to be equal to this. Now remember what we just did. We found the eigenvalues, which are the values for this guy right here, the value that goes in here, because we saw that this can be a solution if this is true, and we just made this true. So we found these lambdas right here, and we found the vector that corresponds to the lambda. Now, because we're saying, hey, well, if my lambda is lambda 1, then my k is related to it once I plug it back into this equation. And so we have to relate each lambda with its own k. And basically, what does this say? Well, this basically says, this is basically the eigenvalue problem. And what the eigenvalue problem tells you, if you rewind back to this expression right here, this is the eigenvalue problem. If I multiply a matrix by a vector, I want to get just a scalar of that vector, which means that vector does not get knocked off of its span during that particular transformation. And these are the vectors that don't get knocked off their spans during the transformation A, which is this matrix right here. So now we know that these are both solutions to the system, and we can use the superposition principle to find the general solution. Use the superposition principle to find the general solution. So we're going to say that the solution 1, x1, is going to be, we have our 2 and our 5, and then we're going to have our e. What was the lambda for that? 1 times t. And our x2 is going to be -2 and 1. E, and it was a -3 for the lambda. And now our general solution is going to be these two added together with some constants in front. Yes, plus C2 -2, 1, e to -3t. Wow, it took a little longer than expected. This was a review for me as well, but I hope you understand how you deal with this one. This one was a case where all of the eigenvalues have independent solutions. And so they don't get mixed up with multiplicity, and we don't have complex eigenvalues. All right, I hope you understood this one, and I'll see you next time.